Well, good afternoon, everybody. I hope that everyone is doing well and safe. This is Chris Kearns with the Office of Energy Resources. This webinar presentation today is to discuss the results of the analysis performed to assess the solar siting opportunities for Rhode Island. As a number of you are aware, we launched this effort last fall and contracted with Synapse to perform this analysis. I do want to express thanks and appreciation to Pat Knight, Aaron Camp, and Caitlin Odom from Synapse for all the effort that they did in putting this presentation together. They will go through the steps for today's presentation and process. Just to let the group know that the PowerPoint presentation and the report will be distributed to the various email listservs that we passed on this webinar announcement to sometime on Wednesday for the group to have access to. It will also be posted on the Office of Energy Resources website and also on Synapse's website as well. With that, Pat, I will hand this off to you to begin the presentation.
Great, thank you, Chris. So hi all, and also I'd like to offer my welcome to our presentation on solar siting opportunities in Rhode Island. As Chris said, I'm Pat Knight from Synapse Energy Economics, and I'm joined today by my colleagues Caitlin Odom and Aaron Camp. And together, the three of us will be providing an overview of our analysis, including our methodology and findings and some important caveats. And we'll have time at the end of the presentation, as well as in the middle of the presentation, to answer some of your Q&A. So first, I'd like to just start with a few logistics. So this webinar is being recorded. As Chris said, we will be posting the recording of the webinar on our website alongside these slides and the report of the analysis itself. And that email with a link to those three documents will be coming out tomorrow. Also, as you may have noticed, everyone has been muted by default. We do want this to be an interactive webinar. We're hoping to get a good number of questions from all of you. If you have questions, we ask you to submit them using the chat feature in Zoom. Depending on how your screen is set up, that chat button is either at the bottom or the top. And you can just click there and type in your question whenever it occurs to you. We'll be pausing midway through the presentation to answer some technical questions at that point, just for 5 to 7 minutes. But we'll have quite a long Q&A session towards the end as well. So just to give a overview of our agenda here, after I wrap up our logistics, I'm going to be talking a bit about background of our presentation. After that, I'll be turning things over to my colleague Caitlin, who will be walking us through the methodology. From there, my colleague Aaron will be discussing the results from our analysis along with several key caveats. And then at the end, before we get to the Q&A session, I'll be talking a bit about solar integration topics, as well as a brief summary of incentives for non-conventional solar in states neighboring Rhode Island. So first, some background about Synapse. Synapse Energy Economics is an energy and environmental consulting firm located in Cambridge, Massachusetts. As Chris said, we were commissioned by the Rhode Island Office of Energy Resources to perform this solar siting study back in fall 2019. This blue box here just summarizes some recent work that's relevant to the study that we're about to talk about. Last year, we worked on a primer of Massachusetts SMART program, and we also worked on a interesting potential study for Washington, D.C. about rooftop solar. But today is all about Rhode Island, and specifically the potential for PV systems in Rhode Island. The main thrust of our study was to estimate the total technical and economic potentials for solar across a number of categories. And these categories include rooftops, including residential single-family, residential multifamily, commercial, industrial, municipal, and other types of rooftops. We also looked at ground-mounted solar in 4 different categories. We looked at landfills, gravel pits, brownfields, commercial and industrial parcels, and finally, we also looked at potential for solar in parking lots or carports. An important caveat I want to mention here is that we did not evaluate any potential for ground-mounted solar on residential or agricultural parcels in Rhode Island. So mainly the first step of our analysis was to calculate megawatt potentials. We were then able to transform those into megawatt hour potentials. And from there to transform those megawatt hour potentials into greenhouse gas reduction impacts. Using recent historical data provided to us, we also provide information on recent costs of solar, as well as just a sort of lay of the land of what has been installed in Rhode Island to date. Our study also dives into information about what other neighboring states have done to promote solar development, but balance it with other land use interests. And our study also goes into some summary of information of current PV policies in Rhode Island. And we'll be touching on all of these in our walkthrough today. So just to give a very high level overview of our analysis, the very first step was to use geographic information systems, or GIS software, to identify suitable areas for solar development in each of the categories identified on the previous page. Wherever possible, we estimated these potentials for all 39 towns and cities throughout the state. Once we had these areas from the GIS software, we then converted those areas into capacity potential, energy potential, and avoided greenhouse gases using spreadsheet post-processing. Throughout this analysis, we relied on many different data sets, one of which included Rhode Island's own GIS clearinghouse on building footprints. We relied heavily on parcel and zoning data that was provided to us by almost all of the towns and cities throughout Rhode Island. We looked to National Grid and Rhode Island Commerce Corporation for information on some of the existing data out there about what has been installed to date, along with existing costs and system sizes. We talked extensively with local solar developers about siting considerations, and we worked with different state agencies, including OER and DEM, on other data sets that were necessary for our analysis. One of the other, or two other data sets were quite important, and we'll be talking about both of those later on. That's the EPA's AVERT tool, which is used for avoided emission factors, as well as recent NREL studies that have been done to analyze the potential for solar throughout the country, not just Rhode Island. I also want to mention our project outreach. We conducted a kickoff meeting right at the start of the project to help frame the analysis and to solicit feedback. And we also did a project update, which garnered some more interesting feedback that we were able to integrate into our analysis. Throughout the project, we were communicating with town planners and state agencies, as well as talking with OER, National Grid, and other groups about existing solar data. We also issued a survey to solar developers in order to garner information on Rhode Island-centric data that might be relevant to the different categories of solar that we were that we analyzed as part of this work. So before we dive into the methodology, I want to just sort of set the stage here. The main point of this analysis was to examine solar potentials for Rhode Island. And in this project, we evaluated 3 different types of potentials. So the very first potential that we looked at is total potential. And you can think of this as the entire area that might be considered for solar PV, excluding any areas that currently have existing solar, but otherwise having no constraints whatsoever. So you can think of this as looking at a parcel of land and imagining that that parcel of land is entirely covered in solar panels with no constraints whatsoever for shading or existing buildings or things like that. The next step down is technical potential, which is a subset of total potential. And this type of potential it essentially removes or screens out areas that are deemed unsuitable for solar. So for rooftop solar, this might include areas that aren't necessarily south facing on a roof, or parts of a roof that have dormers or other types of geometry that impede solar development. Technical screening for ground-mounted solar might mean parts of a parcel that are too close to nearby parcels, or are occupied by wetlands, or are on land that's very steeply sloping. The third category we looked at is economic potential. And this is yet another subset, this time of technical potential. And this is a category that we looked at for residential rooftops only. And it evaluates the amount of solar likely to be installed given financial considerations. And for the purposes of this analysis, we thought about financial considerations such as the current cost of the technology, payback periods given the current incentives that are in place right now, and household economics throughout the state. One important piece of this is there really isn't any bright line distinction between total technical and economic potential. In fact, they're really more of a spectrum wherein you remove different parts of land for either physical reasons or economic reasons that are translated into physical reasons. So in light of this, wherever possible, we have strived to present potentials for all of the categories in the study on an apples to apples basis so that we can actively compare technical potential for landfills, for example, with technical potential to gravel pits. Another caveat I want to mention is that for many of our categories, we present ranges of results. And the purpose of these ranges is to reflect some of the uncertainty in the key drivers we used to develop our potential calculations. The next two slides are cartoons aimed at helping to think about what technical potential is versus total potential, since this is a pretty key part of our analysis. So this first slide is a house, and it's concerned with the siting challenges for rooftop solar that might reduce the amount of total potential and turn that into technical potential. So some of the things that solar developers might have to contend with could include avoiding rooftop obstacles, like I was mentioning, vent pipes and so on, avoiding shading from nearby trees or buildings, situating the solar such that it ideally faces south as opposed to north, and other considerations that might be specific to a building, like the roof age or structural integrity. For ground-mounted solar, I would say that the considerations are a bit more varied. There's a wider set of considerations to take into account. There's shading, again, like for a rooftop, but there's also setbacks, how close you can build your solar to neighboring parcels, things like how steep the slope of the land is, whether the land needs to be remediated or capped in some way. And then there are other considerations like permitting costs, other types of remediation, for example, and other types of construction elements that might go into certain types of ground-mounted solar that might cause the installation to be more expensive relative to a conventional site, but might not necessarily affect the overall technical potential. Our next slide here is about solar installations to date. On this slide, what we're presenting is the installations that we have that were sent to us that reflect all of the installations that have been put in place in Rhode Island through fall 2019. And this covers installations from Rhode Island's REF program, as well as its REG program, and a number of other programs that are listed in the second bullet of this slide. And essentially, to date, there have been about 7,700 installations throughout Rhode Island, which translates into about 160 megawatts. And this is important, or I just want to highlight this here because all of the potentials that we're talking about, total, technical, economic, and so on, they're in addition to the existing solar that I'm showing on the slide. They're above and beyond. So this is just something to set the stage with that we've already considered as we get into our analysis. So next, I'm going to turn things over to my colleague Caitlin, who's going to walk us through the methodology.
Thank you, Pat. Hi, everyone. As Pat already said, my name is Caitlin Odom, and I will be going into more detail on the methodology we used for the 6 categories previously mentioned. I'll discuss how we found the available area for each category, and then I'll explain how we converted that area into megawatts and megawatt hours. I'll begin by discussing the rooftop category, and then I'll follow up with the ground-mounted categories, which have very similar approaches, including the landfill, gravel pit, brownfields, and commercial and industrial. And for the final category, I will discuss parking lot and carport solar. which has the most unique approach of the categories. So let's begin with our methodology for the rooftop area. We started off with geospatial data file from Rhode Island GIS Clearinghouse that provided us with polygons of building footprints for over 300,000 buildings in the state of Rhode Island. This data only contained information on the location and area of the building footprints. So to categorize these buildings, we joined this data with zoning data provided to us by municipalities to then inform what type of building each polygon was. The categories we used are shown in the blue box to the right on this slide. Finally, we classified each building as either small, medium, or large. The final area for each category was then used to calculate the total potential area for solar on rooftops in the state of Rhode Island. Once we exported that total area available, we were able to scale those values to find the technical area suitable for rooftop solar. We used a rooftop solar study from NREL that I will discuss in more detail in the following slides to inform that scaling process. And finally, as Pat already mentioned in the previous slide, we performed an economic potential analysis for residential rooftops in the state. We used a range of costs, incentives, and incomes to perform a payback analysis for solar to find the economic potential for solar in the entire state of Rhode Island. We then took that payback analysis and used the statewide number and scaled it to each municipality based on the income level for each municipality to find the economic potential for solar for each municipality in the state. So next we'll dive into the ground-mounted solar categories. So starting off with landfill solar, thanks to some very helpful folks at the University of Rhode Island, we were able to use the geospatial data for landfills in the state. This data informs the location, total area, and shape of each landfill in the state of Rhode Island. Using this data, we were able to identify the total potential area for solar on landfills for each municipality in the state. Our technical screening is similar for all of the ground-mounted solar categories. We begin by screening out all overlapping building footprints with a 50-foot setback for shading. Next, we screened out any land that's not suitable for solar, and follow that by applying a slope filter, which Aaron will discuss in more detail in the later slides, to screen out areas that are too steep for solar. Finally, we analyzed the area after applying 2 different property line setbacks to account for zoning and shading constraints to find the low technical potential area for solar, shown in green on the right, and the high technical potential area shown in purple. The low and high values were aggregated by municipality to find the technical potential area for solar on landfills for each municipality. So we'll go to the next slide. So next we'll dive into the gravel pit potential. We began with point data from the United States Geological Survey that informed where 13 gravel pits were located in the state. These points were actually locations on streets, so we used satellite data to identify the corresponding parcels for each gravel pit point. Using GIS area calculations, we were able to find the total potential area for solar on gravel pits in the state. To find the technical potential area, we used the same screening approach as landfills that I discussed in the previous slide. So next slide. Moving right along to brownfields, I wanted to start by highlighting the Rhode Island DEM definition of a brownfield as a property where expansion, redevelopment, or reuse of the property might be of which may be complicated by the presence or potential presence of a hazardous substance, pollutant, or contaminant. Brownfields can be any type of property, including commercial, industrial, or residential properties. So Rhode Island DEM also provided us with a data set including the addresses and sizes of over 700 brownfields in the state. After cleaning that data, we were able to match approximately 1/3 of those brownfields to existing parcels in the state. For the largest 14 brownfields that we were unable to match with the addresses using GIS, we added in manually by locating the sites using satellite data and incorporating them into our analysis. Using GIS area calculations again, we were able to find the total potential area for solar on brownfields in the state. Due to the large number of sites, we were unable to manually screen every site for existing solar. So to account for this, after converting those area numbers to megawatts, we subtracted the capacity of existing brownfield solar from our total potential value. To find the technical potential, we used the same approach as landfills and gravel pits, but we did not perform a slope analysis due to the large quantity of data we had here. So next slide. So the final ground-mounted category we analyzed was commercial and industrial. To find the total area potential, we used the zoning and parcel data provided to us by municipalities to identify the location and shape of over 25,000 commercial and industrial parcels in the state. Once we screened out all non-CNI parcels, we were able to calculate the total area potential for solar on CNI. And then once we converted this area to megawatts, we also subtracted out the potential for solar on CNI rooftops to ensure we did not double count those values. So to find the technical potential area, we applied a similar methodology as the previous ground-mounted categories, but like brownfields, we did not perform a slope analysis due to the amount of data we had. Next slide. So the final category we analyzed as part of this project was for carport solar located on parking lots. As I stated in the beginning, we used a unique approach for this category due to the lack of existing data for shape and location of parking lots in the state. To find the total potential, we started with a crowdsourced geospatial data file from openstreetmaps.com. Using this publicly sourced data, we were able to identify a subset of the parking lots in the state of Rhode Island. We then performed a spot check over different sizes of municipalities to estimate what % of parking lots were being excluded from our initial data set. And then we scaled our final values to find the total potential area for carport solar in the state. After we converted that area to megawatts, we subtracted capacity from existing carport solar installations in the state. Then, to calculate the technical potential, we screened out all building footprints with a 50-foot setback to account for shading constraints. Our final calculations for potential were calculated using the best information we had at that time. However, data on carports is extremely limited at this time, and the number of installations has changed since our initial calculations back in the fall. This area would definitely benefit from some additional research as more data becomes available. Next slide. So in all the slides prior to this, we discussed how we calculated the area potential for each category. In this slide, I'm going to explain how we converted those areas into megawatts or capacity and megawatt hours or generation values. As I mentioned earlier, we utilized two major NREL studies to support our methodology and analysis for this project. In the first study, referred to here as NREL 2016A, folks at NREL looked at cities across the United States to analyze the technical potential for rooftop solar. This study was more of a large-scale top-down approach, as opposed to ours, which is more starting from the bottom. In the second study, referred to here as 2016B, NREL 2016B, researchers estimated the economic potential for solar and detailed their assumptions and methodologies. More information on both of these studies and how we incorporated the work already done on this topic can be found in our full report. At a high level, we converted the area potential for each category into megawatt potential using capacity density values for the appropriate category, either rooftop or ground mounted. We then took those capacity potential values and applied a 20% capacity factor for carport and ground mounted solar and a capacity factor low range of 13.7% and a high range of 16% for rooftop solar to find the yearly generation potential for each category. So this concludes the discussion on our methodology. I think we're going to take a brief pause for questions before we dive into discussing the final results of our study with Aaron.
Thanks, Caitlin. Hi, everyone. This is Pat again. We've got a few questions that have come through so far. A reminder, if you have questions, just go ahead and click the chat button or the Q&A button. on your Zoom controls and type in your question there, and we'd be happy to take it. I think we'll spend about 5 minutes, or yeah, about 5 minutes now to answer these questions, and then we'll move on to the results section. So one question that I see posted here is about the pipeline of projects, and it asks, did we look at the pipeline of projects submitted for net metering or remote net metering that are currently in the queue? And the answer there is no. We do have that data, but for the purposes of subtracting existing solar, we are only considered the solar that had been built through fall 2019. A second question is about the brownfields, and this person asks, what about the other 2/3 of brownfields outside of the additional 13 large brownfields? So just to go back to our brownfield methodology quickly, what we had to start with was a data set from DEM that listed 700 different addresses for brownfields, and we were able to successfully match or find the brownfield addresses for about 1/3 of them. So for those 1/3 parcels, we're able to perform technical screening directly within GIS. The data set that we got from DM also has information on the area of the brownfields, if not necessarily the exact location. So what we were able to do for the 2/3 of brownfields that were not able to be identified in GIS, we basically applied a scalar that looked at the ratio of technical potential to total potential for the brownfields we were able to match, and we applied that to the brownfields that we were unable to match. Another person asked a question about whether utility infrastructure interconnection requirements were considered anywhere in the study process. I'll tee that up for a set of slides that are coming towards the end, and we'll be talking a bit about that in greater detail. One person asked, does carport solar include possible construction of canopy covers with solar over parking lots? Yes, that is the definition of carport solar here. Another question that we've gotten is all about the, is really about whether the types of solar that we've considered for brownfields or landfills or gravel pits takes into account whether these parcels are residential. And the answer is for certain parcels in the categories of brownfields, gravel pits, and landfills, yes, it's possible that those parcels might be zoned as residential today, or were zoned at or have been zoned at residential since they were first developed. So those are included in our analysis. However, any parcels that are currently zoned for residential but are undeveloped, or are zoned as agriculture but are undeveloped, were not part of our analysis. Another person asked, does carport solar include parking garage canopies? Unfortunately, we were not able to evaluate parking garages as part of this work, but I believe Aaron has a few things to talk about that in just a few slides. So in the interest of time, I'm gonna turn things over to Aaron so that we can get into the solar potential results. I think that these might get a few more of the questions that I see coming in on the chat feature. Again, we'll have ample time at the end of the study to pause and ask for questions again. So Aaron, do you wanna go into the solar potential results?
Thanks, Pat. First, I just wanna check my sound. Can you all hear me okay?
Yes, I can hear you.
Wonderful. Well, thanks, Pat. Again, my name is Erin Camp, and I have the pleasure of reviewing the results of our study with you. For this presentation, I will be focusing on megawatt potentials. As Caitlin mentioned, we also calculated the megawatt hour potentials in the report, but those potentials are not included in today's presentation. To help ground these megawatt potential results in reality, you can think of about 1 megawatt of solar being enough power for roughly 150 to 200 homes in Rhode Island. And that statistic comes from the Solar Energy Industries Association. So with that, we will jump into the results for rooftop solar. So statewide, we find a total potential of about 3,400 megawatts of rooftop solar potential, with nearly half of that being in the residential single-family category due to the high prevalence of single-family homes in Rhode Island. We analyzed a total of about 367,000 rooftops statewide. The technical screening reduces our total potential to about 25% of the original total estimate, yielding a technical potential of 850 megawatts. About 3 to 5% of residences in Rhode Island are not suitable for any solar, and that equates to about 12,900 households. And we think that that's a conservative estimate, as we did not look into rooftop integrity in this analysis, given the lack of data available for that. The screening for technical potential takes into account rooftop geometry, shading, and rooftop obstacles like any HVAC systems and other factors, as determined by NREL. Next slide. Great. So this slide, and including the maps, focuses exclusively on the total potential for residential buildings. We find that all towns in Rhode Island have at least 13 megawatts of total potential for rooftop solar. On average, a town in Rhode Island has about 90 megawatts of total rooftop solar potential. In general, if a town has more buildings, it has more rooftop solar potential, as exhibited by the left-hand map showing the highest solar residential potential in the Metro Providence area. As I mentioned before, the largest potential rooftop category is residential single family because of the high prevalence of single family residential buildings in Rhode Island. However, as you can see in the far right-hand map, multifamily buildings have the highest potential in Metro Providence area, given that multifamily buildings are most common in urban areas. Next slide. Now moving on to the technical potential for residential buildings. All municipalities in Rhode Island have at least 3 megawatts of technical rooftop solar potential. On average, towns in Rhode Island have about 22 megawatts of rooftop solar technical potential. As I mentioned before, the technical screening reduces the solar potential to about 25% of the total estimate, yielding a technical potential of 850 megawatts. The map shown on the bottom of this slide shows that the residential technical potential for solar is highly concentrated in the Metro Providence area. Now moving to the economic potential for residential buildings. The economic filter reduces the solar potential on rooftops to between 110 to 250 megawatts. Even at the lowest end of the economic analysis, all 39 municipalities in Rhode Island have at least some economic potential for residential rooftop solar. Given the prevalence of single-family homes, the highest economic potential is on single-family homes and results in 90 to 210 megawatts. And on multifamily homes, we find an economic potential of between 20 to 40 megawatts. Now moving on to the ground-mounted solar categories, starting with landfills. Statewide, we calculate that on landfills, there's a total potential of 430 megawatts. When we apply the technical screening that Caitlin discussed, that reduces the total potential to between 70 and 260 megawatts, depending on the setback assumed. For the low technical potential, that is the high setback, or the 375-foot setback. And for the high technical potential, that is the low setback assumed, or 50 feet. Capping status is an important consideration when thinking about whether you can site solar on a landfill. Capping status was not included in the technical potential filter in this analysis, and as a result, some landfills in the technical potential category may require a cap prior to any solar installation. Of the 63 landfills in our data set from URI, 19 of them are currently known to be capped. However, there might be more that we don't know of. About 17 of those landfills do not appear to have a current reuse, and about 12 appear to have at least a partial reuse. Next slide. As I mentioned before, there are 63 landfills that we have identified across 34 towns in Rhode Island. So landfills are spread across the state, and after applying the large setback, the 375-foot setback, 33 landfills remain for the technical potential. So about half of the landfills get removed from our potential analysis results when applying the large setback. Now for the maps. On the left-hand side, we are showing the total potential for solar on landfills. In the middle, we're showing the low technical potential for solar on landfills. And on the right-hand side, we are showing the high technical potential for solar on landfills. The distribution of potential for solar on landfills is highly correlated with the location of the largest landfills in the state. Next slide. Moving on to gravel pits. Statewide, we find that there is a total potential of about 150 megawatts of solar on gravel pits. The technical screening reduces that potential to between 30 and 90 megawatts, depending on the setback assumed. We find that there are 13 known gravel pits in Rhode Island, but only 9 towns in Rhode Island have a gravel pit. As you can see from the map on the left, 1 town in Rhode Island has 3 gravel pits, and the remaining towns either have 2, 1, or no gravel pits. Once we apply the technical filter, only 12 gravel pits remain for the technical potential analysis. Next. Now this map shows the potentials for solar by municipality on gravel pits. On the left-hand side, again, we have total potential. In the middle, we're showing the low technical potential. And on the right, we have high technical potential. And as a reminder, the low technical potential corresponds to the high setback, or the 375-foot setback, and the high potential corresponds to the low setback, the 50-foot setback. The potential results for gravel pits are, of course, strongly correlated with the location of the 13 gravel pits in Rhode Island. Now moving on to brownfields. Statewide, we find a total potential of just over 1,000 megawatts of potential on brownfields. Once we apply the technical screening, we find that there is a technical potential of between 260 to 650 megawatts on brownfields, depending on the setback. And most brownfields are found in the Metro Providence area, as you can see in the map on the left. Moving on. Now for the maps of brownfield solar potential by municipality. The total potential is shown on the left, the low technical potential is shown in the middle, and the high technical potential is shown on the right. And again, the low technical potential corresponds to a high setback, and the high potential corresponds to the low setback. Notably, the potential for brownfield solar does not match where the location of the brownfields are exactly, and that is due to the fact that the largest brownfields in the state tend to be located in the south, where you see the highest potential. Now for our final ground-mounted solar category. This is the commercial and industrial parcels. Statewide, we find a total potential of about 9,000 megawatts, split about half and half between commercial and industrial sites. The technical screening reduces that potential to between 1,200 and 4,600 megawatts, depending on the setback. The commercial and industrial potential is strongly linked to a municipality's land area, but it's also driven by the number and size of parcels that are classified as either commercial or industrial by that municipality. Based on the information that we receive from municipalities, we find that the distribution of commercial and industrial potential is about evenly distributed across the state, as shown in the map on the left. The blue municipalities indicate that the highest potential of solar in that municipality is commercial, and likewise, the brown municipalities indicate the highest potential is on industrial parcels. Now moving on to the maps for commercial and industrial. These maps are laid out a little bit different than the prior slides. On the left-hand side, we have total potential for both commercial and industrial parcels. In the middle, we're showing total potential for only commercial parcels. And on the right-hand side, we're showing total potential for just industrial parcels. And as you can see, the highest concentration of potential on CNI parcels tends to be located primarily in the central part of the state. Next slide. Now these maps focus on the technical potential for CNI, with the low technical potential being on the left and the high technical potential being on the right. And same as before, the greatest technical potential tends to be primarily focused in the central part of the state. Now for the last category, parking lot solar results. Statewide, we found that there is a total parking lot solar potential of about 1,590 megawatts. And once we apply the technical screening, that reduces our potential to just over 1,000 megawatts. These are the maps of the total potential for parking lot solar on the left and the technical potential for parking lot solar on the right. These results indicate that the highest potential for parking lot solar depends strongly on the quantity of parking lots, perhaps obviously. So the more urban a municipality, the higher the parking lot solar potential is on average. Now moving on to the annual avoided emissions and our estimates for costs. In the top table, we are presenting the avoided greenhouse gas emissions per year in terms of million metric tons of CO2 for the technical potential for each category of solar that we analyzed. We came to these numbers by multiplying the megawatt hour potentials, which are in our report and haven't been discussed during today's presentation, to emissions factors taken from the US EPA's AVERT model. For solar, that avoided emissions rate is about 0.57 short tons per megawatt hour. In total, we find that if all the technical potential were to be installed in Rhode Island, there would be an avoided emissions of between 3.47 and 7.65 million metric tons of carbon dioxide per year. Now, to ground that in reality, that equates to about 31,000 to 68,000 gallons of gasoline avoided per year. Moving on to the bottom table, these show historical solar costs, specifically for Rhode Island. These come from data provided to us by the Rhode Island Commerce Corporation and National Grid. For several categories, our data on costs is limited. As you can see, for the 4 ground-mounted solar categories, our estimated costs per watt and per megawatt hour are currently listed as being equal. Now, we know that in reality, these are not likely to be equal, but given the limited amount of data, this is our best estimate for approximate costs of installing solar on those ground-mounted categories. Parking lot costs are based on a very small number of data points, as Caitlin mentioned previously, and they are higher, we think, due to the greater infrastructure required for installing solar on parking lots on top of, on carports on top of parking lots. And these costs may change as the technology matures. This slide shows a case study of incremental costs at what we are calling non-conventional ground-mounted sites. We spoke with a solar developer from Rhode Island called Rhode, and they provided us with their estimates of incremental solar costs for one of their installations in Warwick. This is for a 6.3 megawatt installation at a combination landfill brownfield site, and their estimates are provided in the table at the right. When looking at incremental costs across several different categories, Rhode estimates that their incremental costs for developing solar at a non-conventional site is about 13 cents per watt. And when comparing this to our historical solar costs on the previous slide, we find that Revity's incremental cost estimates are about 4% above median costs. We want to caveat that this is the experience of a single installer at a single site, and more data is needed to better quantify incremental costs at non-conventional sites. That concludes the overview of our solar potential results. And now I'm going to focus on some caveats to the solar analysis. As you can probably imagine, this was a very large lift, and we relied on many different sources of data across many different sources. And for that reason, not all the data is of equal quality, and not all the data came to us with full completeness, so that required us to make some assumptions along the way to the best of our ability. I am going to present some of the major caveats from our report, and for some of the more detailed, smaller ones, I'd like to refer you to our report. So starting with the rooftop analysis, we used building footprint as a proxy for rooftop area, which we believe slightly overestimates the rooftop space. And furthermore, we did not include structural integrity of rooftops, as I mentioned previously, because of the lack of data available for that quality of roof. So our estimates likely include roofs that are not structurally suitable for solar, again, which probably slightly overestimates our results. For both rooftop and C&I categories, out of the 39 towns in Rhode Island, Synapse received zoning and parcel data from 34 of these towns. For the 5 remaining towns that we did not receive data for, we used available data from comparable towns and scaled based on population size and density. For carports, our analysis does not take into account parking lots that are adjacent to tall buildings, which would increase the necessary setback due to shading. If we had taken into account tall buildings, that would have reduced our total carport potential. Furthermore, analysis does not include parking garages, which would have increased our estimates. Now moving on to the primary caveats for ground-mounted solar. The setbacks were determined using input early on in this project provided by solar developers in Rhode Island. Using this input, we determined that we should assume the need for a 50-foot setback from all buildings and a property setback of between 50 to 375 feet. As a result, we conducted our technical potential analysis with these two boundary conditions, 50 feet and 375 feet, to represent the range of technical potential. Slope was considered in our technical potential filter as described by Caitlin. We assumed a limitation of 10 degrees or less based on feedback from solar developers early on in the project. And we used LiDAR data converted into a digital elevation model, which we input into our GIS software and then applied the filter of 10 degrees or less. For gravel pits specifically, we used an original US Geological Survey dataset from 2003, and this may exclude newer gravel pits in Rhode Island that we currently don't know about. So our estimates may be an underestimate of true gravel pit potential. Similarly, for landfills, the original dataset comes from URI and was dated 2005 and may exclude newer landfills. And furthermore, we were not able to manually check the accuracy of URI's shapefiles relative to satellite imagery for every landfill, given the sheer number of landfills in the dataset. Finally, on landfills, because the dataset is relatively old, our dataset may not reflect true capping status, and it may not reflect current potential reuse of landfills. So some landfills in our analysis may already have been reused for some other end use other than solar. Moving on to brownfields. Our data set only includes remediated brownfields rather than all brownfields. So therefore, our analysis may be an underestimate. Our analysis also likely includes some sites that have already been repurposed or are planned for redevelopment or some other purpose, in which case our estimate may be an overestimate. Moving on to CNI, despite our best efforts, there is likely still some overlap between our potential results in this category and our potential results for the brownfields category because of the unmappability of all brownfields in the data set. That concludes the primary caveats from our analysis. And again, I encourage everyone to read the full report for more details on all of the study's caveats. And that concludes my portion, and I'm happy to take questions.
Thank you for that, Erin. I do see some questions coming in. If people don't mind, I think it'd be best to get through the next couple of slides since a number of the questions deal with the topics we're about to dive into. And the Q&A session is probably about 10 to 15 minutes away. So please continue to submit your questions and we'll look forward to talking about them in just a couple of minutes. So the next couple of slides deal with solar integration topics. The very first one that I'd like to bring up is a slide that shows solar technical potential as it relates to electricity sales throughout the state. So this is to help give an idea of the amount of technical potential we're calculating from all the categories relative to the current electricity sales in each one of the towns and cities. So for purposes of comparison, 19 of the 39 municipalities have technical potentials that in aggregate either match or exceed electricity sales. Now, this comparison isn't strictly apples to apples, since solar generation doesn't necessarily match hour by hour electricity consumption. But I think it is useful in terms of just illustrating the scale of the solar potential on an annual basis. My next couple of slides are all about hosting capacity, and I think these get at some of the questions that I've been seeing coming through on the chat and the Q&A functions. So I want to spend a good deal of time on this, since it sounds like it's an area of interest to a number of people. So in November 2019, Synapse received data from National Grid on hosting capacity of distribution lines throughout the state. This data set lists the hosting capacity for 3-phase lines throughout Rhode Island. This data set also contains information on the location and an orientation of 1- and 2-phase lines, but no statistical or numerical data about those smaller feeder lines. This data set was really primarily concerned with the 3-phase lines. Each one of these 3-phase lines has some amount of information attached to it. Information might include things like the current distribution capacity that's installed today, the maximum hosting capacity that might be available at any one point on the line, as well as the minimum hosting capacity that might be available at any one point on the line. Importantly, this data doesn't necessarily say where these maximum minimum points are. Before I get into the actual analysis of our hosting capacity, I do want to just highlight a few more of the data challenges that we were working with here, because it did limit our analysis in some ways, and in other ways it really steered the analysis that we were able to do in terms of comparing our hosting capacity, or the hosting capacity data that we had, with the technical potential data that we were able to calculate. So in addition to not necessarily knowing where the maximum or minimum hosting capacities were on any one line, the lines themselves are often very large. Sometimes they span across 2 towns, sometimes they span across even more than 2 towns. So performing this analysis with this data set on a municipality by municipality data basis is very difficult, very challenging. One more caveat I want to highlight here is that the data received from National Grid represents the hosting capacity at a certain point in time. This hosting capacity can evolve as the distribution grid changes, as it's upgraded, or as more distributed generation gets added to it. So I would caveat this analysis as being a snapshot analysis of the hosting capacity data that existed as of last fall, but not necessarily the hosting capacity that might exist at the end of this year, for example. Hosting capacity, the last caveat I'll mention before we really get into the analysis here, is that hosting capacity shouldn't necessarily be viewed as a physical barrier to solar, like zoning setbacks or slope might be. In many situations, upgrades to the distribution system can be performed. However, these upgrades cost money, and in some cases can be very expensive compared to the relative price of the solar facility being proposed. So because we can't discern what the hosting capacities are for each individual town, it's impossible to say with absolute certainty what the actual hosting capacity is compared to the technical potential. However, with that limitation in mind, we have performed a series of analyses that help to compare at least the technical capacities versus the technical potential capacities versus the hosting capacities. So the first such analysis we did deals with what we're calling a project perspective. In this analysis, what we've done is examined the maximum hosting capacity for any one line within each one of the municipalities. So the map that's in the center of the slide here shows the 3-phase lines all across the state. And what you can think, one way to think of this analysis is saying, if one town has 5 lines crossing its boundaries, what is the maximum available hosting capacity from any one of those, from all of those lines put together. So that's what this chart on the right here shows, or this map on the right here shows. And according to this map, there are 21 towns or cities that have a maximum hosting capacity of at least 8 megawatts somewhere in the town. Now, there might be situations where there might be multiple lines that each have their own hosting capacity of 8 megawatts or smaller or larger. But on the other hand, there might be some situations where the hosting capacity for a particular line occurs in one town, but not the next town. So for these lines, it's impossible to, again, assign with any certainty the absolute hosting capacity to one town or the other. So there are sort of error bounds on both sides of this perspective. In our next perspective, we looked at what we're calling a policy perspective. And in this analysis, we're comparing the range of aggregate technical capacities across all of the categories that Aaron was just walking us through against the range of hosting capacities for each town. So I'll ask folks to focus on this bar chart in the lower right-hand corner here. And according to this chart, roughly speaking, if there is a yellow bar that is completely below or within the pink bar, it means that today's hosting capacity range for that town is sufficient to accommodate all of the technical capacity for solar that we calculated. On the other hand, if the yellow bar is above the hosting capacity range, either entirely or partly, it means that that town's hosting capacity is currently insufficient to accommodate all of the technical capacity that we've calculated for that town. Again, important caveats here. Just because we're calculating very high technical capacity for certain towns doesn't mean that that capacity can be installed or will be installed. And just because the yellow lines might be above or well above some of the pink bars, even in those circumstances, the data suggests that the hosting capacity can still accommodate at least some technical capacity of solar. So again, I wouldn't necessarily call these two analyses the final word on the subject. Instead, we're thinking of them as being more indicative in terms of for which towns, how does the technical capacity that we've calculated stack up against the hosting capacity that's been reported to us with the data that's available. Before we go into the Q&A session, I want to talk briefly about some incentives for non-conventional solar in neighboring states. So the first state I'll talk about is Massachusetts. Massachusetts has a SMART program that offers a tariff-based incentive for 10 or 20 years, depending on the system size. And the SMART program is very, very complicated, but the easiest way to think about it is depending on where a solar facility is proposed in the state of Massachusetts, that facility can receive some incentive payment that's paid in terms of a dollar per kilowatt hour amount. And that dollar per kilowatt hour amount can vary depending on the type of land that the solar facility is built on. So for example, if a solar facility is proposed to be sited on a brownfield or a landfill, there are incentive bonuses associated with those land use types. On the other hand, Massachusetts has identified certain land types as being greenfields. And for these land types, the solar that would be proposed would be awarded a subtractor that would reduce the incentive relative to that same facility built on some other site. New York has a similar policy in place for brownfields and landfills in terms of awarding an additional incentive for solar sites that are built on these types of preferred land uses. However, New York's incentive is a dollar per watt basis. Vermont also has an incentive for brownfields and landfills, and it shares more in common with Massachusetts, just in the sense that it's a dollar per kilowatt hour payment rather than a dollar per watt payment. Now, this is an exhaustive list of incentives for brownfields and landfills. there are other federal or state level funds available. In some situations, these funds or policies might be directed at clean energy that repurposes contaminated sites. In other cases, like this program from EPA, the Repowering America's Land Initiative, it's all about brownfield redevelopment, but is not strictly limited to renewable redevelopment. So that brings us to our Q&A session of the presentation. We've gotten a lot of comments in so far. I noticed a few people have their hands raised. You can just go ahead and type your question in the Q&A button or on the chat button, and we'll answer them as we go. And if you have specific slides you'd like us to go back to, please just type in the number of the slide you'd like us to go to or the title of the slide, and we're happy to cycle back to that. So through this Q&A session, I'm going to be playing the role of moderator. If there's a question that comes in that seems most related to the parts of the presentation that I presented, I'll be fielding those. In other situations, I'll be passing the questions off to Aaron, Caitlin, or Chris, depending on the questions that we get back. So one of the first questions I see says, were local solar ordinances, moratoriums or restrictions already imposed, et cetera, captured anywhere? The answer to this is no. The data that we got from different municipalities on zoning and so on didn't necessarily have this information in there. So in the case of municipalities that have moratoriums in place or restrictions in place, we would probably view the technical potentials that we've calculated as part of the study as being an overestimate relative to what could be built in those towns given the moratoriums or restrictions. Another question here is asking about solar potential in Central Falls and why there doesn't appear to be any solar potential in that city. And the answer is that there is solar potential in Central Falls, but it's largely in the rooftop category. Central Falls, as we all know, of course, is very small and very densely populated. So there are few opportunities for the ground-mounted solar categories that we've been talking about. To make this question about broader than Central Falls specifically, in the report and in appendices to this document are detailed tabulations of solar for solar potential across all the categories that we analyzed. So if there's a particular municipality that you're interested in for gravel pit solar or rooftop solar or so on, you can go to that appendix and read all about it. One attendee asks, are you able to assign uncertainty values in megawatts to the estimates? So this is something that, Aaron, I think you might be well equipped to talk about in terms of the differentiation between the high and low cases or amounts of solar potential in each of the different categories we talked about.
Yeah, absolutely. So for the total potential category, you are right. We did not do any sort of calculation on sensitivity or uncertainty. However, for the technical potentials and the economic potentials, we provided a low and a high estimate to reflect the uncertainty in those categories. And that was the best approach that we could think of to reflecting uncertainty in the analysis.
Thanks. So to continue with our questions here, there's another question here about the setback of 375 feet and the idea that this might be overly restrictive for many municipalities. So one of the challenges that we're faced in this study is that we're dealing with 39 different towns and cities, and each one of them has a different set of zoning requirements for the different types of zoned elements that are in that town and city. Generally speaking, the setback estimates that we're talking about here are rough estimates. Every town and city is going to be a little different in reality. This 375-foot estimate is large, and it's because it's a setback number that takes into account not only zoning requirements, but it is also intended to take into account shading requirements, so shading from nearby trees. And I'll offer that there is a quite extensive discussion of this in the report itself. So if this is a topic that you're very interested in, I recommend checking out the report, and there's a lot more information in there. There's a question here asking about, in our consideration of residential rooftop solar, whether we're considering the full rooftop area or whether we're limiting our potentials to be just enough to offset each building's annual usage. We don't have data on each individual building's annual consumption. I understand that for the REG program, there is a limit on the solar potential that can be generated from each building, in the sense that it can't exceed some percentage of the annual consumption. That wasn't something that we were able to take into account, just given our lack of data on individual buildings. There's a question here about a basic summary table providing the economic potential for rooftop residential solar. Unfortunately, we don't have that table in our presentation, but it is in the executive summary of our report. So again, when we're sending that around in the next day or so, you'll be able to take a look at that and learn about economic potential both for the state as a whole as well for individual towns. There's a question, excuse me. There's a question here about the three-phase lines. And the person asks, even though three-phase lines were not seen as a barrier, does that mean that a parcel could have been 10 miles from a three-phase line, but passed the technical screening of slope and setbacks? So the answer to that is yes. We performed all of our technical potential analyses except for hosting capacity first, and then the hosting capacity analysis after that. And the reason for that is because each category, whether it's rooftops or gravel pits or landfills, they all impact hosting capacity in aggregate. And so what we were aiming to do is to try to compare the aggregate potential across all the categories relative to the total hosting capacity within each municipality. The other part of this question addresses the distance for different parcels from the three-phase lines. And again, that's just a limitation of our data. There's just so much of it. It's impossible to say for any one parcel how close it is to a particular three-phase line, or in other cases, whether there are two or one-phase lines even closer that could be suitable for interconnection. Another person asked, how do we get access to the report? We'll be posting the report along with this slide deck and the webinar recording probably first thing tomorrow. We'll be sending around an email to all of the people that have registered for this presentation, as well as other listservs that OER might have. So there will be quite a wide distribution of that. So you should see that in your inbox probably tomorrow morning. One question here asks whether equity, such as access to solar for all, was considered in this analysis, and how. Unfortunately, we were not able to get to the equity question. But I think this might be worth diving into our economic potential analysis in a bit more detail, because I think it might answer some of the questions there. So for our economic potential analysis, we started by looking at residential rooftop solar, and we looked at the costs of solar as it exists in Rhode Island today, and the incentives that are currently available for rooftop solar, residential rooftop solar today. using a combination of the incentives and assumptions about typical usage patterns for electricity and so on, and the information on the current technology cost, we were able to develop a range of payback periods for different types of customers who are participating in different incentive programs. Using an NREL study, we were then able to translate those payback periods into adoption rates. So this isn't a real number, but just for example, if a payback period was 10 years, then an adoption rate might be 50%. If a payback rate was 12 years, then an adoption rate for an area might be 20%. We then applied this adoption rate to the state as a whole. After that, we wanted to reflect the fact that different municipalities throughout the state do have different financial, or different households throughout the state have different financial access to solar. So we looked at the median household income for each municipality and scaled the adoption rate relative to each municipality's median income relative to the statewide median income. So this is one situation where I think that there are a number of other directions that you could have gone in terms of thinking about equity and access to solar with respect to different households' financial situation. But I'd encourage you to take a look at the report and learn more about our economic analysis there to see if that perhaps answers some more of your questions. I see another question here that is about rooftops that are structurally suitable. And the question asks, what percentage of rooftops do you estimate are structurally suitable? Erin touched on this in her portion of the presentation. Erin, do you mind just talking a bit about that?
Sure, I'm happy to.
And as far as data availability and that sort of thing goes?
Yeah, so we have said already that we didn't have access to data that gives us a sense of which rooftops or how many are structurally suitable for solar. So that's why we weren't able to include it in our technical filter. So unfortunately, no, I don't have an answer for you on what percentage of roofs are not structurally suitable in Rhode Island. But my best estimate would be to use building age as a proxy for rooftop suitability.
Right. So in some states, again, I just want to mention that this study deals with a number of very large, disparate data sets. And unfortunately, one of the data sets that we don't have is information about each building's age. In some states, that data is available. In Rhode Island, it was not. So this is one area that I think could be developed depending on data that might be available from different state agencies or perhaps the towns themselves on building age. And with that information, I think Erin's absolutely right. That would be a good proxy for structural suitability and would help to hone the numbers in some more about the residential rooftop potential. This same commenter asks, what percentage of sites do you estimate have feasible interconnections available? Again, this is a data limitation issue. Because of the type of data that we received on hosting capacity, this type of information wasn't available to us. Finally, this commenter also asks, do you analyze the impact of wetlands on potential sites and the associated setback requirements? Wetlands were a land type that we evaluated or that we used in our screening for technical potential. So any parts of parcels that exist as wetlands or other unsuitable building types such as beaches, rock outcroppings. There are others that I can't remember off the top of my head. Those were all removed from our analysis and cause the total potential to shrink as it goes to technical potential.
Pat, can I just add one quick thing there?
Yeah, of course.
To provide a little bit more clarity on the setbacks, we did not look at any setbacks around the boundaries of wetlands. We only looked at setbacks from the property line.
There's another question here that says, what policy changes would you recommend for Rhode Island to maximize solar siting in these preferred areas? Chris, do you mind taking that one?
Yeah, thanks, Pat. So the Office of Energy Resources, in terms of this reports and analysis, will certainly help those conversations prospectively in terms of we have already made some modifications to the programs known as the Renewable Energy Fund, administered by Commerce Rhode Island, and the Renewable Energy Growth Program, most recently in terms of the inclusion of Carport based incentives. And we know that there have been a handful of Carport projects awarded over the last couple of months as we begin to develop projects on existing parking lots in different parts of the state. But also this report highlights it just in terms of the setback criteria that we hope that municipalities will look at this report and the different results for each municipality, which will be reflected in, as Pat noted, the appendix of the report and breaking out what the megawatt numbers translate to in each municipality. It will be important in order for the state to maximize a number of these locations, in that when they adopt either first-time solar ordinances or possibly make modifications, that they avoid one-size-fits-all type ordinances as it relates to setbacks or lot coverage, and that if you apply the same standard, you could potentially hinder the development of these locations. So we hope this information will be helpful for municipalities to have access to help inform local decision-making on their respective ordinances.
Thanks, Chris. So there's a few more questions. If you haven't submitted any questions yet, again, feel free to do so using the chat function or the Q&A function. Those are buttons either at the top or bottom of your screen. So another question that's come in is asked about forecasts of economic potential. So do you make any forecasts about how much economic potential will change over time? For example, 10 years from now, considering changes in cost, rates, and income. Unfortunately, that wasn't something that we took into account in our analysis. I'll note that one of the other pieces that might change over time aren't just the technology costs, but also the incentive costs. And all of these factors might play together or might relate to one another in order to create different economic potentials pictures for, say, 2025 or 2030. There's another question here about wetlands. If the parcel was made up of 5% wetlands, was this parcel discarded? And the answer is no. We only screened out the portion of parcels that were wetlands or one of these other unsuitable building types. So if you, in this particular situation, if it was 5% wetlands, we are assuming that solar could be constructed on the other 95% of the parcel, assuming that other 95% didn't run into some of the other technical barriers, such as slope or setback or existing buildings. So I think that's done it so far for questions that I've received here. I'm just going to go to the next slide and put up email addresses both for myself and for Chris. We still have time reserved, so if you have questions, feel free to keep sending them in. But here's our email addresses and our phone numbers. So if you have any questions about the report that we worked on, feel free to just shoot us an email or give us a call, and we'd be happy to talk more about that or clear up any clarifications that you might want answered.